So I would like to, it's my pleasure to introduce our speaker of our seminar today is Sam Nariman from Purdue University. Sam is interested in many questions of topology, and in particular, this talk is much related to our seminar and our previous project with one related to cohomology of diffeomorphisms group and characteristic classes. And the title of the talk is on local and global invariants of flat bundles. So please, Sam.
Yeah, well, thank you very much for the invitation. It's a great pleasure to talk about this topic to like-minded people. I'm excited that some people are interested in cohomology diffeomorphism groups. Okay, so this is going to be very relaxed talk. I'm gonna talk about some motivations and some work in progress about characteristic classes of flat bundles. But let me start with the classical story and the work of Milner. So Milner's work on Lie groups. Okay, well, feel free to stop me whenever you feel to. So let G be a Lie group, a finite dimensional Lie group, in fact. And when I write G delta, I mean the same group. It's with discrete topology. Okay. So what Milner was interested in was, if I say it in a moduli theoretic way, suppose that you're interested in principal G bundles over X, some topological space X, up to isomorphism. Okay, so that's one moduli theoretic problem. Another one is surprisingly when you put a connection with a flat structure or a vanishing curvature, so flat principal G bundle over X up to isomorphism, and this is a forgetful functor. This is also moduli theoretic problem, and from topological point of view, there are classifying spaces that classify these structures. As you probably know, the right-hand side is classified by space called BG. That there are some models for BG, but just roughly. Oh, is this screen for you out now? Shall I? Well, let me know if you.
No, it's back now.
It's back now. Okay, good. So there are different models for BG, in particular one constructed by Milner, but BG is just the one universal construction is you find a contractible space on which G acts freely and properly, and then you take the quotient. And so saying that BG is a classifying space means that, if you map X to BG, it gives you a principal G bundle over X, and any homotopy class of maps gives you isomorphism class of principal G bundles. And it's actually elementary, but to my taste, surprising that also flat principal G bundles have classifying spaces, and it's the same construction, but for the discrete group. And then there's a map from BG delta to BG. It's usually denoted by eta in the literature. And so this is the forgetful functor in this language. And so this map has been studied extensively in the context of algebraic K-theory. So let me just say a few things about this map. So one theorem due to Milner was that if G is solvable, then eta star, so the map between cohomology of BG with finite field coefficients to cohomology of BG delta with finite field coefficients is an isomorphism. Okay, and in fact, he made this conjecture. It's a famous conjecture, still widely open, that this is true for any Lie group, for any real Lie group. So the evidence for him is just for the solvable, but the conjecture is for any Lie group. And there are some stable results, for example, for GLNC or SLNC. This is known up to a range, but still widely open. Okay, so you see, there is this finite field coefficient phenomenon, but when you go to characteristic 0, this was observed by Milner that let's say G is compact. So G compact, then the cohomology of BG, say with real coefficients or rational coefficients, to cohomology of BG delta, this map, again, eta star, is trivial. So although we expect that with finite field coefficients, it's isomorphism with characteristic 0 coefficient, we expect that in most cases, even when G is not compact, like if it's, you know, semi-simple complex Lie group, it's going to be trivial. And if it's not complex Lie group, real Lie group, then this map is mostly trivial. And in fact, there is a theorem, another theorem, Milner, that exactly says what the image is. So, but you see, there is this dichotomy between finite field coefficients and real coefficients. And in fact, when you work with real coefficients, there are two more fundamental things that I would like to say about this. So one actually goes back to Milner, but it was vastly generalized by Gromov. So let me tell you the version that Gromov proved. Gromov proved that if G is algebraic group, then this map eta star from cohomology of BG with real coefficients to cohomology of BG delta with real coefficients. He proved that eta star, the image of eta star, lies in bounded cohomology. Okay, so note that the cohomology of BG delta is is the same as group cohomology. So if I write H star of G with real coefficients, I don't mean as a space, I mean as a group cohomology. So group cohomology. And when you when you think about group cohomology, you can consider those cocycles that are bounded. So R is your coefficient. There is a, the usual metric on R. You can talk about bounded numbers. If you consider those cocycles that are bounded on G, that's a cochain. You can take its cohomology. It's going to give you bounded cohomology. And the observation of Gromov was the image of this guy, whenever it's non-trivial, it's going to land in the bounded cocycles. Okay. That's one interesting observation about the image of this map. And in fact, there is a fundamental diagram.
Sorry, may I ask you, if you say G algebraic, you mean with Zariski or you topology or not?
Yes.
This BG with Zariski, thanks.
Yes. Yes, thank you. And if you consider continuous cohomology of the group, there is a different story. And let me say it as a fundamental diagram. And this fundamental diagram, I try to fit it in this part of the page. Hopefully I can do that. So let me say the cohomology of BG delta with real coefficients, the cohomology of BG, again with real coefficients. So there's a map like this. And remember, we had this map from BG delta to BG eta. Let me call the fiber of this map BG bar. So we have this fibration, and then you can further go to cohomology of BG bar, again with real coefficients. So the fundamental diagram is, when G is nice enough, finite dimensional Lie group, then you have Chern-Weil theory, calculating the cohomology of BG for you. So this is sometimes called invariant polynomials on the Lie algebra. And then there is a Lie algebra cohomology, relative Lie algebra cohomology of G with maximal compact. So this is maximal compact. And there's a map from here to here. And then there is a absolute Lie algebra cohomology. And there's a map like that. And it goes to cohomology of BG bar. And as I said, in nice cases, the bottom map is an isomorphism, like when G is compact or semi-simple complex Lie group. The middle map is again in nice cases injective. So this is injective, say for semi-simple complex Lie groups. And similarly for the first map. And in fact, not only it's injective, it's isomorphism of Van Est, that this is isomorphic to the continuous cohomology of G, say with real coefficients. So when G is nice enough, it says the continuous group cohomology injects into group cohomology of G. And the point of continuous group cohomology is that it's easier to calculate because it's given by the Lie algebra cohomology. In the cases of bounded cohomology, as you probably know.
Sorry, may I ask you again, this HJK, usually Lie algebra cohomology is with respect to a representation. And here you write K as a group, so it is not a Chevalley-Armberg cohomology of the G. Or
it's a well, you could make sense of it as a Chevalley-Armberg cochains, relative cochains, or you could just think of it as like
there is an adjoint representation acting. No,
you could think of it as invariant forms on G mod K.
Yeah.
Yes.
Okay, thank you.
That's a different way. But yes, there is an adjoint representation. You can consider invariant cochains that way. And yes, so I said that continuous cohomology is easier to calculate because of Van Ness isomorphism. In the case of bounded cohomology, the bounded cohomology is most of the time notorious object to calculate, and it's widely open whether it injects into group cohomology in almost any example. But I'm going to talk about some cases that are known. Okay, so that's the basically history of finite dimensional Lie groups that I would like to mention. Any questions so far? All right. So if not, let's talk about the diffeomorphism group. So now let G be just diffeomorphism group of a circle. Circle is the simplest, I guess, manifold to start with. And already for diffeomorphism group of a circle, the story is rich enough. So here are the fundamental diagram for diffeomorphism group of the circle. So let me write it here. So cohomology of B diff of S1. I'm not going to write the coefficient. I mean real coefficient for the time being. The cohomology of B diff delta of S1 and the cohomology of B diff bar of S1. Okay, and in fact, as a topological group, suppose a diff is C infinity diff. So I'm not going to write the regularity now. As a topological group, this is homotopy equivalent to its subgroup of rotations. So in fact, it's so everything is orientation preserving, by the way, and it's in fact homotopy equivalent to rotations. So B diff of S1 is the same as BS1, and the only thing that is there is Euler class. So there is a map from polynomial on Euler class to cohomology of B diff of S1. This is the Euler class. And the flat S1 bundle, on the other hand, it's the corresponding group here is the relative Lie algebra cohomology, continuously Lie algebra cohomology of vector of S1 relative to SO2. So vector of S1 is the Lie algebra of diff, and this S1 is the maximal compact subgroup. Here is the continuous Lie algebra cohomology in this infinite dimensional setting, and here is the the absolute Lie algebra cohomology of vector of S1 to here, and actually, what is interesting here, I said this is isomorphism. This is not hard. The same thing holds here, and that's a non-trivial theorem. So this map is injective. This is Morita. I forget which year, something like 83 or 85. and this is also injective. So the fact that this injects in all degrees is a non-trivial fact. So one thing that was known already by Thurston, it was known by his thesis that the second homology of diff delta of S1 surjects to Z plus real numbers. Surjection to Z comes from the Euler class, and surjection to R comes from the Godbillon-Vey class. And so that's only for H2, and conjecturally, the above map is isomorphism. But Morita's theorem is in all degrees. In particular, as a corollary of Morita, he gets this thing that the powers of the Euler class.
Since there is again a problem with the screen.
Oh, this gadget for some reason gets disconnected. Sorry for that.
No problem. I have the same problems all the time with it.
Yes, I mean you have remarkable too. It's not remarkable in this direction. Okay, there we go. So corollary of Morita is the powers of the Euler class are all non-trivial in the cohomology of BDF of a circle. Okay. For all K. Okay, that's a non-trivial statement. And let me go back to the theorem of Thurston and say one more thing about what we can prove about diff of a circle. That, as I said, story about the circle is already a non-trivial story. It's a very hard problem to say that, to calculate the homology or cohomology of B diff discrete of a circle completely. Already for H2, saying that it's an isomorphism to Z plus R implies deep facts about foliations. Okay, but this conjecture comes from this idea that the only invariance that we could build for flat circle bundles is either the Euler class or this invariant that comes from foliation, which is the Godbillon-Vey class. And because of the lack of other invariants or our imagination, we say it's probably isomorphism. And one thing we recently proved was actually in this direction. We proved that there is no more class that is bounded. So if there is anything else other than Euler class and Godbillon-Vey, it has to be unbounded class. So theorem joined with mono is that the bounded cohomology of diff of a circle is in fact isomorphic to the polynomial ring on the Euler class. So I don't want to spend too much time on bounded cohomology since this talk is not much about bounded cohomology. I would like to tell you more about continuous or smooth cohomology of diff. But but these results about the bounded cohomology of diff to me is quite surprising, because calculating bounded cohomology for discrete groups is usually very hard. And any technique that is available is either about H2 or H3. And basically, in bounded cohomology, there is no example known for finitely generated groups that you can calculate bounded cohomology completely if it's not zero. But somehow for diff, although it's a huge group, calculating bounded cohomology becomes approachable. And we could calculate for a couple of manifolds, in particular some spheres. I'm just going to mention maybe one more result in this direction. That the bounded cohomology of diff of S3. So this is again mono and myself. This is 0 for star less than or equal to 4. This is interesting because it says that the Euler class, so as a corollary, the Euler class and the first Pontryagin class are not bounded for flat S3 bundle. Okay. This was a question by a TNGs that asked whether Euler class is bounded for flat S3 bundle. So this is a somehow non-constructive way to answer G's question, that these classes are not bounded. Okay, so back to this fundamental diagram for diff of S1. So we know that there are Godbillon-Vey classes, there are Euler classes, and we said that if there is anything else, it has to be unbounded. And as you probably know, Godbillon-Vey class is known to be unbounded. I mean, there are examples by Thurston, like flat bundle over just surface of genus 2, whose Godbillon-Vey class goes off to infinity. So that makes it unbounded. Okay, and there is a Van S type isomorphism for diff of S1. So this is in fact isomorphic. This relatively algebraic cohomology is in fact isomorphic to smooth or continuous cohomology of diff of S1. This is very special to diff of S1 because normally for diffeomorphism group there's no maximal compact like finite dimensional Lie groups, in a sense that G mod the maximal compact is contractible, but this is the case for diff of S1, and you can run the same argument to get Van Est type for diff of S1. Okay, but let's go to the story of continuous cohomology, the remaining time. So continuous, or sorry, I'm going to say smooth cohomology following Losik, smooth cohomology of diffeomorphism. All right, so so let me remind you some fundamental theorems that I'm going to use, which is the theorem of first of all, it's a so suppose that M is a compact manifold. Then when M is compact, you can consider the Lie algebra of vector M. So Lie algebra. This is in fact Lie algebra of diffeomorphism group of M when M is compact. And then you can ask about Gelfand-Fuchs cohomology, which is continuous Lie algebra cohomology of vector M. And this has been calculated. So I'm going to tell you what this is. But to say what this is, I need to introduce some objects first. Cohomology. Okay. So the story is, suppose that you instead of compact case, you just think about Rn, and you try to figure out what the Lie algebra cohomology of vector of Rn is. So Gelfand-Fuchs. Gelfand-Fuchs calculated the Lie algebra cohomology of vector of Rn. In fact, if you consider germ of vector field at the origin, it gives you what is called the formal vector fields, and they have the same Lie algebra cohomology, it turns out. So if you look at the literature, it's usually denoted by Wn. This is called formal vector fields. They have the same Lie algebra cohomology, and this is isomorphic to the real cohomology of some space, and I'm going to denote by Yn. I'm going to tell you what Yn is in a moment. And Yn is the following space. Consider the universal UN bundle over BUN, and consider the 2n skeleton of BUN. And then take the pullback of EUN over 2n skeleton. That's going to be Yn. This is pullback. And Gelfand-Fuchs theorem says that the cohomology of formal vector fields is the same as the cohomology of some space with real coefficients. And it was conjectured by Fuchs that one can somehow globalize this isomorphism over a manifold, and that's in fact the case. So the theorem that is due to Hafliger and Bott and Segal independently is there is an isomorphism of the Lie algebra cohomology of vector M with the real cohomology of some space that I'm going to denote it by, I'm going to write sections. It's a section space of some bundle over M, and this bundle is described as follows. So I'm going to write M and consider the frame bundle of M and twist it with Yn. So twist with the On action. This is with real coefficients. Okay, so frame bundle has On action and Yn also has On action. This is because going back to the definition of Yn, so Yn over 2n skeleton is in fact UN bundle. So there's a free, so Yn is in fact admits a free UN action, so in particular admits a free On action. So you consider the space of sections of this bundle, and this is isomorphism. This is isomorphic to the Lie algebra cohomology of vector field on M, which is very interesting statement. But in particular, it says that this, there's some sort of local to global phenomenon when you want to calculate the Lie algebra cohomology on vector fields. Okay. So when you want to consider the same story for any manifold, you have the cohomology of B diff bar of M, again with real coefficients, say. You have the cohomology of B diff delta.
So Sam, sorry, again disconnected.
Oh my goodness. Sorry about that. Well, feel free to ask questions while I'm trying to reconnect. Okay.
Oh, fine.
B diff delta of M and cohomology of B diff. So suppose that you want to reconstruct the fundamental diagram for any manifold. The thing is, as you probably know, cohomology of B diff with the usual topology is already a complicated object, and it's an object of active research for different manifolds. Even disk, calculating the B diff of a disk is a deep direction of research in high dimensions. And we know that, well, B diff discrete and B diff bar are just harder than B diff. So it's just a harder problem to do that. And so there is no candidate to put here. There's a candidate to put here, which is just the Lie algebra cohomology of vect of M. So that's the only part of the diagram that we can fill in if you want to have the same sort of diagram of characteristic classes. But already this point of view, I just want to say that this already has some consequence of proving non-vanishing results. So let me tell you one thing in this direction. So I have about 15 minutes. Is that accurate?
22, usually we have 1 hour. So
okay, so I have about 20 minutes. Okay, so I'm going to use the remaining time to tell you about the theorem of Losik. So, so let me first say something that is somewhat elementary. So if you have a bundle, suppose that you want to build a characteristic class for a manifold bundle. So you have E over B, and the fiber is manifold M. Okay. So if the M is compact, then what you can do is to build a class in the cohomology of E, and then fiber integrate to get a cohomology get a class in cohomology of B. So we usually denote it by pi lower Schrick that goes from the cohomology of E to cohomology of B shifted by the dimension of M. So let me say the dimension is N, the cohomology of B. So now if you assume that E is flat, then you have basically two sources of characteristic classes. One is to forget flatness and then build some invariant in E and then fiber integrate, or use some invariant of the foliation and then fiber integrate. Okay. So if E is flat, then we have, you know, invariants like Godbillon-Vey class. So so for example, you probably are familiar with this notation that like H C1 to the 2n, sorry, C1 to the n, if the codimension is n. Is a class in H 2n plus 1 of E, using the codimension n foliation. And then you can fiber integrate along M. H C1 to the n is going to be a class in Hn plus 1 of B. And you can ask whether this class is non-trivial. Okay. And this is already a non-trivial question for higher dimensional manifolds. One thing that I proved many years ago was for surfaces. So for example, theorem, if you have a surface as M, say sigma G, E, and then B, this is a pi. If you integrate, you know, H C1 squared over sigma G and H C2 over sigma G, they are in H3 of B, and they are non-trivial. They are non-trivial for the universal example. I want to use the idea that I used for this to reprove a theorem of Losig, or sketch a different proof of theorem of Losig for you, to sketch how you can use a local to global phenomenon to prove non-triviality of characteristic classes. Okay, so what is the theorem of Losig that I'm talking about? Losig said the following. So similar to what I described here, said consider consider the, so I'm gonna say it in a different way. This is not how Losig said, but it's equivalent. So consider the universal M bundle, flat M bundle. So it's going to be B diff delta of M as a base, and then you have the universal space over it, and then with a fiber M. So this is a universal flat M bundle over the classifying space. Okay, so what does that mean? That means that it's, in particular, it has a codimension n foliation. So when you have a codimension n foliation, you get a map to the classifying space, the universal classifying space of codimension, singular codimension n foliations, which is called Hafliger space. If you don't know what Hafliger space is, it's fine. Just believe me that there is some classifying space for not codimension n foliations, but singular codimension n foliations, that has all the properties of the characteristic classes. So all the universal characteristic classes, they already live in B gamma n. So now, whatever characteristic class you have here, you can pull it back to E, and then you can push it forward to B diff delta. Okay. It turns out that one can make sense of the smooth cohomology of B gamma n. And this is isomorphic. So there's some sort of Van Est isomorphism. This is isomorphic to the relatively algebraic cohomology of formal vector fields with ON relative to ON. This is again Van Est type isomorphism. So I can pull back the classes here to E and then push them forward. So then that means that I could define a map from relatively algebraic cohomology of WN to the shifted cohomology of B diff delta of M. Since this is smooth cohomology, it factors through the smooth cohomology of diff. And Losik says that this is injective, when star is bigger than 2n. So this is Losik. Okay, so I want to tell you why this is the case, using some local to global idea. Any question about the statement? No? All right. Okay, so let me go to a new page. You see, I have, let me tell you how I think about E, the universal bundle. So I think about E as the manifold M homotopy quotient by diff delta. This is a different way to say this. It's like, the contractible space on which diff acts freely times M and then quotient by diff. Oh my goodness. Again, sorry. Sorry, I should complain to Remarkable. There we go. Okay. So this is how I think about the universal bundle, and so this is a universal bundle over B diff delta of M. Okay. If you pull it back to B diff bar, you have trivial flat bundle. So there is a following picture. So this is like cross M, and then you have a map to M homotopy quotient by diff delta of M, and then they both have universal codimension n foliations. So they have mapped to B gamma n. Okay. I'm going to tell you why it's good to go to B diff bar. Remember, B diff bar was the object in the fundamental diagram that we could fill in the left-hand side for it using the algebra cohomology. Okay. So the way that I want to, going back to this map, the way that I want to prove that this map is injective is to detect it by something, right? So if you have a class here, you map it to here, you want to detect it to say that it's non-trivial. And if you think about the formal vector fields, they already, tell you that because you're thinking about formal vector fields, they are local objects. So if they turn out to be non-trivial, they should be detectable locally. Okay, so what I do is note that if you have a manifold, say this is your manifold, and maybe this is your maybe this is an open set U, some disk at the end. So having a disk in M gives you a map from diffeomorphism group of a disk relative to the boundary. So this is rel to boundary. And this maps to diff of M by just extending by identity, right? So you just extend by identity outside. Okay, so this induces a map from cohomology of B diff delta of M to B diff of a disk, dn delta. And also, when you think about B diff bar of M. Okay. So now let's see whether we can detect these classes by going to a local disk. So I have a map from relatively algebraic cohomology of formal vector fields with ON. Well, this maps to absolutely algebraic cohomology of formal vector fields. By Gelfand and Fuchs, this is isomorphic to the real cohomology of the space Yn. Okay. Well, by a suspension map, I can map this to shifting by n of the n full loop of Yn with real coefficients. Okay. On the other hand, well, before I move on, let me tell you why I went to n full loop of Yn. So what is this object? Why is this relevant? You see, if you remember, we had this Hafliger Bott-Segal isomorphism that says that, so Bott-Segal says that the cohomology of vector, compactly supported vector Rn, so it was for any M, in particular compactly supported vector Rn, satisfies the theorem. It's going to be isomorphic to the cohomology of real cohomology of some section space. So it's going to be cohomology of the compactly supported sections on Rn, the bundle, which is the frame bundle of Rn, and then twisted by Yn. okay, with real coefficients. But compactly supported sections of this bundle, since Rn, the bundle over Rn is trivial, compactly supported sections, it's just compactly supported maps from Rn to Yn, which is just n-fold loop. Okay. So far, so good. So now, if you go back to this picture that we had here, embedding a disk into M, not only you have, embedding of diff into diff of M, you also have embedding of a vector fields to vector of M. So there's a map from compactly supported vector of Rn to vector of M. So this induces a map from cohomology of vector of M to the Lie-algebra cohomology of vector of M to cohomology of compactly supported vector of Rn. Okay. So now I want to use this map to detect the non-triviality of the class. So I'm going to, well, it seems that I only have 3 minutes. Let me speed up. So I have the map from WON with ON to homology of WN, and then to the shifted cohomology of n-fold loop of YN. Here, I also have a map to similar to the version that we defined. It's a fiber integration to go to B diff bar of M. Okay. This is actually too smooth. And then this turns out to be isomorphic to cohomology of vector of M. This goes to cohomology of compactly supported vector of Rn. And this is isomorphism. Okay. This is a calculation that goes back to Gelfand and Fuchs. It's used also in Losik's paper that this is injective when star is bigger than 2n. Okay. So in order to prove that the left-hand side map, the vertical left-hand side map is injective, it's enough to prove that the composition to the cohomology of vector of compactly supported vector of Rn is injective. So I go the other way around. So I say, okay, well, this map is injective when star is bigger than 2n. I only need to care about this map. Okay. But as I said, this is isomorphic to the cohomology of Yn. So this boils down to thinking about the map from the cohomology of Y with real coefficients to cohomology of n-fold loop of Y, say Yn, with real coefficients, shifted. And this map is injective. This is injective. This is not true for any space. This uses the fact that, we should note that rationally, so if you do rational homotopy theory, Yn is wedge of spheres. the fact that Y is wedge of spheres, when you n-fold loop on wedge of spheres, you can see on each sphere this is true. If you let Yn to be, sphere, say, of dimension n+1, and then you n-fold loop on it and then calculate this map, you see it's injective. And when you take wedge of spheres, it's just going to be my vectors. Okay, I'm out of time. Maybe it's a good time to stop. Thank you.
Thank you very much, Sam. Please, some questions, comments. Igor.
I have a question. The frame bundle was not orthogonal frame bundle. It was GLN bundle.
Yes, I should have said that.
Okay.
That's right. Yes, thank you.
Please, some more questions. I would like to ask, so in fact, I'm confused with this. What is the difference between smooth and continuous cohomology for these classifying spaces? As I understand, in logic paper, there were continuous cohomology, and you formulate for smooth cohomology.
Well, it depends on the theory that you use. There is no I guess in the literature, there is no specific theory for these infinite dimensional Lie groups that you say smooth or continuous. The one that I use is only for B-diff bar, and I didn't tell you what it means to think about the smooth cohomology of B-diff bar, because I didn't define what B-diff bar is, other than saying that it's a homotopy fiber of that map. But you could think of two different theories that, to me, one I didn't note both of them by smooth cohomology instead of continuous cohomology, but it depends on your taste. One thing you would like to have is to define the theory so that the smooth cohomology of B-diff bar calculates the cohomology of vector field on M. So I would like to define the theory that is natural enough, and you have this isomorphism. So one theory in that direction is done by Hafliger, and he called it differentiable cohomology. And the way he did it, he defined differentiable cohomology for any, for groupoids, in particular, Lie groupoids and étale groupoids. And it turns out that if you consider, diffeomorphism group, discrete, acting on diff, so this is a groupoid, and so if you use the differentiable cohomology for this groupoid, you have that isomorphism. So this is a theorem of Hafliger, so in his notation, H star diff of this groupoid is isomorphic to the Lie algebra cohomology, so vector M. But on the other hand, this groupoid realizes to be diff bar. So if I call this groupoid curly G, then as a remark, B curly G is homotopy equivalent to B diff bar. So that's one theory, that it gives you this isomorphism that I want. There is another way to think about smooth cohomology of this object, and that's a theory of Brown and Sharba. So Brown and Sharba they have a different theory to think about these things. I'm just gonna, so they don't call it differentiable, they call it continuous. So I'm going to tell you what this is briefly. So if you consider G to be d of M, okay, you can consider a smooth singular set. So smooth singular set of G, and then divided by G. This is a simplicial space. Okay. And then they have a theory of continuous cohomology for simplicial spaces. So I'm just going to call, the cohomology, Brown and Sharba cohomology of this guy, the smooth cohomology of G. So this smooth cohomology, this smooth singular set on G divided by G, if you use the topology of G, the usual, Whitney topology and diff and so on, and the smooth cohomology on the singular set as a mapping space. So it's got a topology, it's a simplicial space. And if you consider it as a simplicial space and consider its cohomology, this is also isomorphic to the cohomology of vector fields, it turns out. This is Brown and Sharba's theorem. So Brown and Sharba's paper, it's about continuous cohomology of simplicial spaces. So if you feed in that theory something that comes from the smooth structure on diff, then it's just a matter of language whether you call it continuous cohomology or smooth cohomology, because you use the smooth topology on diff, and then you say, oh, in that topology it has to be continuous. So anyway, depending on which theory you use, you actually have this isomorphism in both theories, which is essential in the argument.
Okay, thank you. Maybe some more questions. Okay, Sam, thank you very much for a very interesting talk. So we continue the seminar next week.
Well, thanks for the invitation.